Hey there, universe nerds. Tonight, we're turning back the clock, way back. Not billions of years, not even millions, but to the very beginning. The moment when light itself first broke free and filled the universe. That light is still around us today, faint but everywhere, whispering the story of creation. It's called the cosmic microwave background, or CMB, and it's the oldest light we can ever see, the afterglow of the Big Bang. Let's rewind to about 13.8 billion years ago. In the beginning, the universe was hot, dense, and blindingly bright, a soup of particles, photons, and radiation all tangled together. Everything was so energetic that atoms couldn't even form. Electrons and protons were constantly colliding, scattering light in every direction. The universe was like an opaque fog. But as it expanded, it cooled. About 380,000 years after the Big Bang, temperatures dropped for electrons and protons to combine into neutral hydrogen atoms. Suddenly, light no longer bounced around. It could travel freely for the first time. That moment is called recombination, and the light released then is the CMB we detect today. Over billions of years, that light has stretched as the universe expanded. What began as scorching ultraviolet and visible radiation has been red-shifted into the microwave part of the spectrum, invisible to our eyes, but detectable by radio antennas. The CMB now fills the entire sky at a temperature of just 2.725 Kelvin, barely above absolute zero. It's faint, but it's everywhere, a uniform glow that comes from every direction. If your TV ever shows static between channels, a tiny fraction of that noise, less than 1%, is the CMB, the echo of the birth of the cosmos. The discovery of this ancient light was almost an accident. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were testing a microwave antenna in New Jersey. No matter what they did, they kept hearing a faint, persistent hiss. They thought it might be noise from the equipment, even pigeons nesting in the antenna. But after cleaning everything and recalibrating, the noise didn't go away. It was coming from everywhere in the sky. Around the same time, a team at Princeton University was preparing to look for exactly that kind of signal, the theoretical afterglow of the Big Bang. When they compared notes, they realized what Penzias and Wilson had found: the cosmic microwave background, the first direct evidence of the Big Bang itself. That discovery changed cosmology forever. Suddenly, the Big Bang wasn't just a theory, it had an observable fingerprint. The CMB was the leftover light of creation, frozen in time. Later missions, like COBE, WIMAP, and Planck, mapped it in incredible detail. They revealed that while the CMB is almost perfectly uniform, it's not completely smooth. There are tiny temperature variations, differences of just 1 in 100,000. Those slight ripples are crucial because they show where matter was denser in the early universe, the seeds that eventually grew into galaxies, stars, and planets. Every galaxy in the night sky can trace its ancestry back to one of those tiny fluctuations in the CMB. When scientists mapped these fluctuations, they found something astonishing: the cosmic fingerprint of the universe's structure. The distribution of those ripples matches what theories of cosmic inflation predicted, a rapid expansion that smoothed out the universe just after the Big Bang. The CMB doesn't just show us what the universe looked like 380,000 years after it began, it gives us clues about what happened in the first fractions of a second. In those faint microwaves, we can still see the echo of inflation, the shape of space itself, and the balance between dark matter and dark energy. The CMB also serves as a kind of cosmic reference frame. By measuring tiny shifts in its frequency, astronomers can tell how fast Earth, the Milky Way, and even entire clusters are moving through space. It's how we know our galaxy is traveling at over 600 kilometers per second toward the constellation Hydra, the same region as the great attractor we explored earlier. The CMB is our universal backdrop, the canvas against which all cosmic motion is painted. What's amazing is how much we've learned from such a faint signal. The CMB tells us the age of the universe, its composition, its geometry, and even its fate. It shows that the universe is flat to within a fraction of a percent, that dark matter makes up about 27% of the total energy, and that dark energy drives its accelerating expansion. Every precise number we use in cosmology, from the Hubble constant to the density of atoms, traces back in some way to this ancient light. But there's still mystery within the glow. Some features of the CMB, like a strange cold spot that's much larger than expected, don't quite fit the standard model. Could it be a statistical fluke or evidence of something beyond our universe, perhaps even the imprint of another cosmic bubble from a multiverse collision? No one knows for sure. Even in its near-perfect smoothness, the CMB holds subtle anomalies that hint the story of the universe may be even stranger than we think. So, what is the cosmic microwave background? It's the universe's oldest memory, the first light that ever shone, stretched and softened by time, but still echoing through every corner of space. It's our window into the past, the evidence that we're all part of a single, expanding story that began in fire and continues in silence. When we look at the CMB, we're not just seeing light, we're seeing time itself, frozen in motion, whispering the words, "This is where it all began."